So I think what we do is start just any general questions that y'all have. We're all up here. You got climate modelers. So my other colleague, Rob Kafelanos, works in the Office of Natural Environment, and he works on a lot of this, a lot of the environmental climate resilience projects, the pilot projects, Gulf Coast 2, all the stuff that came out of our environmental office. Rob's the expert in that. So I'll just let people fire questions. If you don't, I'm going to have to ask some softball questions here. So
I have one real quick. So looking at the NOAA Atlas 14 data, they showed some trends in either way, but they decided to keep it stationary. So when we're talking about global models and looking forward to 2050 or 2100, 30 or 80 years out, that's great. Can we use anything? Do we ever look back 30 years and say, look, we saw this change occur? Do we ever have any kind of validation, or are we always kind of looking forward? To give us some confidence.
Well, I know Andrea, sitting in front of you, actually looked at the update of NOAA Atlas 14 Minnesota and noticed quite a difference in the preset values from then till now. So
I know some of the areas where dust went down just because you go from 40 years worth of data to 70 years worth of data, or whenever they updated it. To get the 100-year storm event based on just a bigger data set.
Well, I can add to that. And CDOT, Colorado Department of Transportation, did an evaluation using the downscale data, looking at it from a historical perspective, and it reaffirmed the difficulty that the climate model, and they were not using the data set that we're recommending. They were using the BCCA data set, not the LOCA data set, but that it did not, in the historical record, produce the extreme 24-hour precipitations that the measured data did. So I've come across many cases of anecdotal evaluation of the historical record that bears that out, and made some proposals to FHWA as well for doing some further testing on that.
Sorry, you said it bears out that it didn't validate the model?
It bears out that the global climate modeling output is not able to produce the extremes. And I mean extreme in the engineering sense, 100-year, 50-year, not extreme in the climate science sense.
Sure. Definitely for that. For the 10-year, okay, that we're talking about as using the global modeling for the 10-year, looking out 30 or 80 years, would we ever look back 30 years for the 10-year, the less extreme than the 100-year? Or is that still too extreme?
That's something that I would strongly recommend is done. But again, the anecdotal information that I have seen from the CDOT study and others is that 10 years is close to the sweet spot and the extent of what the climate models can reproduce. I don't know if you have some thoughts on that, and so that's one of the reasons that we picked the 10-year as being what we're calling the index value.
and that might be different, Jared, if you've got somebody doing a regional climate model as opposed to statistically downscaled, which is what Roger's talking about.
Yeah, so the plot that I showed with getting the uptick of between the different resolutions versus, so I had the 36, the 12 kilometer simulations. Those are historical simulations that actually, what we downscale is what's called reanalysis data. And so we take, and basically that's like our best observing state of the entire three-dimensional aspect of the atmosphere. And then we try to take that, which is, these products are publicly available, and they call them things like INCEP, in-car reanalysis, or ERA interim reanalysis. But we take these data sets, and then we feed them into our models and try to go to the higher resolutions to see if we can go back and say, can we simulate that, you know, return period that we're interested in? And so we've gone back, and that's what we did in that I was showing is it's like when you go to those short durations, with our best modeling strategies, and this is something that I've been working on, is trying to develop techniques in terms of what just like probably that a lot of you guys do when you do modeling, it is an art to some degree. And so there's some things that you do in the modeling that helps you produce the best results, and trying to figure out how to do that. And so to be able to provide confidence, and that's what we're trying to do. But we clearly know that when you go to subdaily in particular, these are real challenging problems for us in terms of the science community. I do want to go back to another thing that I think is pretty important in talking about stationarity. So when we're thinking about stationarity, and if you think about it from a purely atmospheric science standpoint, that's not going to happen, okay? So let's get that pretty clear. That's not a good assumption. But like Roger said, at times we're limited because our models just aren't able to do everything. And so sometimes, everything can't be perfect. And I think, like Roger said, sometimes you don't want to defeat the good for trying to get the perfect, going towards the perfect. You want to balance these type of challenges. But I think we need to think about how to think about non-stationarity issues. I think that's very important because, as I mentioned earlier, as you increase the temperature of the atmosphere, the saturation vapor pressure increases. So the amount of moisture increases. And there's a scaling ratio that's not linear. And so we know that it's kind of like an exponential curve type of thing. So we know that this is not a linear relationship. And but what do we do? And I don't know how we get about it besides trying to go to higher resolution climate modeling, unless you take approaches like Roger's doing now and saying, hey, given the data that we have, let's try to do the best we can, and then maybe at some point we will be able to update our techniques. And I do have some recommendations in terms of doing that. I mentioned this pseudo global warming experiment. I think that this is a very unique technique that the climate modeling can do. Roger said, well, we didn't select the dynamical models because we didn't have a bunch of global climate models that they downscaled. Because there's a limitation in the number that you can do because they're so expensive to do in our regional modeling. And so the thing about it is, how do you get around it? I think the pseudo global warming is a back way around some of this, but there's some caveats that go along with that, in that they're not really trying to think about, I told you about these thermodynamic versus changes in the circulation. We know the circulation is going to change. And so in the future climate, we know that the storm tracks, for instance, are going to shift possibly further north. And there's a physical mechanism behind that. But if you assume stationarity, or you assume the pseudo global warming experiment, you may not get all of this information exactly right. And so you may be not designing to what you might actually happen. And so I think we need to think about techniques, and I strongly encourage maybe the community to think about using pseudo global warming. And actually there's an experiment by NCAR that's called CONUS 1. And this is a pseudo global warming experiment at 4 kilometers. And I think that there's a potential that, I don't know how we can use it because it's limited in terms of its number of years that's available. I think it's only like 13 or 14 years. And so developing IDF curves off of such a limited number of years is a problem, but I still think we can think about how to think about designing using these type of modeling experiments that maybe are not traditional.
So Roger indicated one option would be to wait until you have a better either climate model or downscaled model. My question is, how do you know when you have that better model? I mean, how do you define that? Because I think Jonathan's question here was, have we been using any kind of data sets to corroborate our existing models to kind of feel more confident in them? And I thought I heard the answer was, well, we've kind of attempted it, but they haven't worked all that well. Maybe correct me if I'm wrong, but the question is, how do you know if we decide to take a wait and see approach, how do we know when to stop that approach and recognize we have a better model that could be used?
I'll start out with saying that we are relying in our work in this project for consensus amongst the climate science community. And so when the climate science community says, at least this is my understanding, that these models are producing 1 hour information that we can use in engineering analyses and design, that's when that time is. And Jared made a comment in an earlier session about the silos. For the most part, the climate science community hasn't been in touch with the engineering community about what the engineering community is looking for. And I think those conversations are now going on thanks to the efforts of Federal Highway and other groups. And so now they understand more of how their data is being used for good or ill. And but my answer is that it's up to the climate science community to say when that time is.
I think everything in research is stepwise. You know, you make incremental improvements, and at some point, decisions need to be made. And if you can make a potentially more informed decision from things that like Roger's doing, I think that's great. I think we can't wait, and I don't think it's a good idea to wait, because I feel like potentially we're on a path that we're going to keep a continuing increase in greenhouse gases, and that's going to be a potential issue. And so I was just reading a paper earlier today, and they were talking about, you know, thinking about current administration, and if we delay and the rest of the world delays, then potentially we're on a more destructive path than we even thought about in terms of potential climate change. So I think it's great to think about adaptation, and always stepwise adaptation, in terms of taking the best available information, and then as it gets better and as we improve it, then we improve our techniques at some point.
Yeah, I would just add that, you know, part of the implication of the question, I hope it isn't to say that we should be waiting for the perfect model, because we're never going to have the perfect model. We're beginning to have tools, and we have had tools for a while where we can start doing these things, so we should apply what we have now, learn from those experiences. As the models get better, we can apply those models. But clearly, the climate is changing. It's evident going forward. I think Jared already talked about this, the fact that the thing that's the clearest is that temperatures have started to go up, and none of the models, none of the scenarios talk about temperatures going down, and that drives the climate system. That will affect everything else. There's obviously a lot of uncertainty on how precipitation comes out, and we're developing methods to address those and understand that. But if we try to wait for the perfect solution, it'll be too late, I'd say.
Are there gross changes to the climate system, like the meandering of the jet stream, or you're talking about slowing large-scale systems, the migration of large-scale systems? Are there others that would be good to be paying attention to?
Yeah, so what you're talking about is, they call it Arctic amplification. And basically, what that process is doing is it's basically the jet streams driven by the tropics being warmer than the poles. And so you get a thermal wind, actually, and that drives the jet stream. And as you start warming the poles more than you do the tropics, then there's this big question about, well, how does that impact the jet stream? And so you're talking about these jet streams, and we all know that probably if you watch the weather or whatever, these are your troughs and ridges that you see on your weather maps and things like that, and they drive the weather. And there's a possibility, there's some thought about how these systems could, as the jet stream potentially weakens, that there'll be more meanders, and so the weather patterns could stall. There's other processes that we have to be concerned with, and one of them that I'm working on trying to understand is the North Atlantic Subtropical High, and this is semi-permanent high-pressure system in the subtropical Atlantic, and how does that respond to climate change? And one thing that the models are showing is for instance, this pressure system is supposed to intensify in the future climate. And if this thing intensifies, it has implications in particular along the East Coast and the Southeast U.S. And it could have implications for storm tracks, in particular hurricanes. And so trying to understand these physical processes is something that climate scientists in particular are thinking about. This is really getting into the climate dynamics, that trying to really understand the processes that could change in a future climate. So yeah, there's definitely different things that people study and different, like the Bermuda High or the jet stream and things like that.
Yeah, I just want to hear a little bit more about the modeling. Like, what exactly are the parameters you use? Are you saying like 4 kilometers? I'm assuming that's a grid, and since you got vertical in there too, so is that a 4-kilometer cube? And can you make it, like, if you want to look at one place more dense, like, does it all have to be one side?
That's a complicated question, so there's different models and there's different techniques. You saw, you guys, I've noticed, have different types of meshes. For instance, the quadrilateral versus the icosahedron, the triangle type stuff. And there's definitely advances in the atmospheric community where you can go down and use like an icosahedron and kind of mesh down at a very fine level over a given region. But those are kind of cutting edge things. So in typical, you basically kind of wrap like a quadrilateral type thing. There's different projections and things and maps that depending on what we do, but there's also 3-dimensional aspect, and you have to prescribe those levels in your models, and you say, how many levels do you need? And when you get to these regional climate model efforts like I'm talking about here, we tend to try to figure out what's happening in the lowest levels of the atmosphere, and we want to really resolve those processes. So we'll stack our model layers, and that we'll put more into lower layers of the atmosphere. And so it's not like when we stack them, they're kind of that same increment. They basically, sometimes we stack them and we try to really resolve the boundary layer processes that are important, such as you think about mixing heights and things that basically you have updrafts and downdrafts that are originating from the surface. So, but yeah, these are different. Some of them are global. What I'm talking about is regional climate models. And so you can kind of go down to even finer and finer resolutions. I mean, people even go down below 1 kilometer in some simulations for, cities, and looking at something like urban heat islands and how they may impact and how they may change. And so you're looking at land surface properties and things like that, and the model can see those things. The weather models can. Hopefully that answers your question.
So I'd like to, is this on? Yeah. I'd like to just ask a question. There's a lot of information that's been talked about today. I don't think Federal Highway is expecting each hydraulic engineer to be a climate expert. And I know in the 1561 project we're making some recommendations, and I just want to get a sense from the panel, if you're a DOT, as an agency, how would you approach this problem? Are there things that you would do more broadly across your state or a region, as opposed to each and every single culvert and bridge being designed to have its own climate study? So maybe y'all could talk about that.
Well, I think my ideal would be for precipitation to create a projected NOAA Atlas 14. That takes resources to do that, and that's essentially what the Canadians did. Is they created their precipitation atlas. That was the approach that Jared mentioned, and that's what was done in New York. Although they use some rather severe scenarios and don't have any moderate scenarios, so it has limited value in my opinion for that reason. So as a state, so that engineers don't have to become climate scientists, to have some sort of what we call programmatic resources developed that an engineer could consult in a table or a online database or something like that. That won't be immediate, which is why we're also talking about these very simple things. But the number, in terms of state DOT guidance, recognizing that not all projects are the same. Not all projects require you to, they're not risks associated with them. The consequences of flooding are not life-threatening. So looking at those risks with each project to determine if you should be concerned about it or not, and looking at your confidence limits for existing data now is also something that I would think a state DOT would want to look at.
Go ahead.
A follow-up to that. With FFRMS being kind of rescinded with the new executive order, for states like mine in Texas, you know, how do we present the idea of looking at climate science and future projections? You know, kind of what strategies would you recommend taking?
How do you sell it?
Yes.
Yeah.
How do you sell it?
I thought about this. Actually, I'm dealing with this because I'm a climate scientist and I live off soft money. So I think there's actually a back way in, and it's really thinking about extremes. And if you highlight extremes and thinking about, because that's what we're really trying to focus in on. And you don't, when you say extreme precipitation, maybe you don't even have to put a context of climate change, because inherently that's what we're really talking about anyway. So I think a back way in is really trying to consider extremes in the future. So you don't have to say climate change, you just think about extreme events. I don't know, maybe others have thoughts about that.
Let me address it from a sea level rise, Saul. It's not a back door, it's a front door. We know these projects are going to be exposed to these sea levels. So you just put it in your calculation like you would, in the old days, we just assumed the sea level was the same when we worried about storm surge. Now we know the sea level's rising and we still have to worry about storm surge. So I think it's just in the numbers coming in the front door, and I think it's the same for the rainfall, Roger.
Yeah, I think that's a very good point. I mean, we can look in the historical record for sea level rise, and you can see that it's rising. I think that's the importance of what Stacey's doing too, in terms of identifying trends and trying to attribute them, because that, depending on how they're attributed, it may be a way of getting in the front door too.
I think just coming at it from a different perspective, I think there are two key messages that you can use in terms of trying to sell the idea of actually embracing these issues and trying to get at it. One is just the issue of public safety, that to the extent that we're not addressing these issues, then the emergencies we have in the future will likely be worse. So the threats to loss of life are higher. And the second is long-term costs, thinking about life cycle costs for assets over their lifetimes. To the extent that we can address some of these issues as we're building things initially, ideally we'll save money over the long term, and that matters to everybody, feds and states alike. So.
And I don't know if y'all heard Joe earlier in the week, but these are things that engineers have been doing since the 1950s and 60s. I don't know, Joe, if you want to say anything. There is existing legislative reasons why we continue to do this and why you can go forward with incorporating extreme events into your designs. And I don't know, Joe, do you want to say anything?
Probably said too much. I mean, when we first started the interstate systems in 1956, it was a requirement to look at future conditions, hydrologic conditions. And so why we look at watershed changes, developmental changes. We look at ultimate development conditions already when we're doing our analysis. This is just another type of manifestation of that kind of philosophy. And the second thing, and Brian alluded to, the other thing you can go to is that you have the authority, statutory authority, to consider extreme events in your design. I mean, that was done by MAP 21, and it essentially allows you to consider that classification just like you would consider seismic retrofits, or you might look at some other thing that you're anticipating some future condition. So the arguments that they make, I think, are probably better or more compelling. But we certainly, I have no problem going to anybody and saying, look, I'm a hydraulic engineer. I've been considering change in future conditions my entire career, and this is just another manifestation that I want to take a look at.
bridge is going to face some type of hydrologic or hydraulic condition, then I know that I don't have to keep on putting more funds into that bridge to maintain it. So it's just a compelling, you know, Rob said, a compelling safety issue, compelling economic issue, and a compelling, basically, philosophy that we, you know, collectively have been incorporating for years and years and years. So, yeah, I think, you know, I'll be glad to talk to your bosses too, you know, because I do think it's just, we'll be penny wise, pound foolish, otherwise, and we'll just throw away 70 years of what we've been doing as a transportation community for important transportation assets.
So it's just a hard sell since NOAA assumed, in Atlas 14 at least, assumed stationarity. You know, and that was relatively recent. So that is, I completely agree that precipitation is changing, but when we're talking to our bosses and, you know, the last big publication came out and said, stationarity probably exists, but we're going to ignore it because the record of data, the noise in the record of data snows climate change. It's hard to bump that up another 20%.
I was talking to my boss, who's kind of having that kind of thing. I say, you know, the planning folks say that my watershed is going to have this much development in 25, 50 years. And, you know, and maybe they're talking to planners that, you know, they're making projections just like the climate scientists are making projections. I can't say you're going to have that development watershed. So if we're accepting it on a planning point of view in terms of what's going to happen, in terms of what we're expecting, in terms of, hey, you know, we have to build additional capacity in our roadway because we're expecting to have some type of increased population in this corridor or whatever. That's the same argument I would take to, you know, to my bosses and say, yeah, you know, we can go back and say, well, no, Atlas 14 stationarity, and that's fine, but we know that things are going to be changing. And so why don't we basically kind of take that and run? I mean, panel, please correct me, because you're up there, I should be, you know, back out that door or something like that. So,
There's a paper that came out about risk-based decision-making under non-stationarity. And it says, you know, well, maybe the science says there's stationarity or there's non-stationarity. You know, we saw from the flood trends map that sometimes it goes up, sometimes it goes down. This is variable across the landscape. But when we look at those trends and we say, well, there's a trend there and our flood peaks are increasing, there's two types of errors we can make when we talk about there's a trend. There's what we term a type 1 error. And that's where we say there is not a trend, or there is a trend. We say there is no trend when there actually is. Wait, no, that's type 2 error. There is not a trend when there is a trend when one actually exists. So that's okay. Let me start over. This is kind of confusing. So the type 1 error says there is a trend when one does not actually exist. Okay, and so that's the type 1 error, and we can actually specify that confidence in our trend calculations. The type 2 error is what we cannot put a confidence on, and that is variable depending on the trend magnitude, our length of record, the variability in the data. And so what you say with the type 2 error is a trend exists when we say it does not exist. And so what are the consequences associated with the type 1 error? Often, you know, overinvestment, over-design. And so that's the consequence. Well, what's the consequence associated with the type 2 error, where we can't specify a consequence and it's sort of dependent on the data? Well, that has certain societal consequences that could cost us, you know, infrastructure dollars or lives, depending, you know, on what type of structure or infrastructure we're dealing with there. So there's two types of errors that we have to consider when looking at these trends.
So I wanted to bring it back to kind of more of a policy area and how states can do things internally. So I wanted just to ask for a raise of hands, like how many people are involved in the asset management process within your states? So states had asset management plans, initial ones due a few months ago in the summer, and the final full plans are due next June. Within the asset management plan, asset management is all about maintaining assets at a state of good repair over the long term at least cost. At least that's my simplified definition of it. Part of it looks at considering life cycle costs and considering life cycle costs for groupings, like logical groupings of assets like coastal bridges, for example. And those life cycle costs are supposed to consider a range of risks. And one of the risks that states are supposed to look at is including extreme weather events and climate change, as well as all sorts of other risks that states may face, like budget risks, political risks, economic risks. So I would suggest, one of the, we talk a lot today about the issue of breaking down silos. One of the good things, the asset management program or the asset management plans that states are doing could be one of those areas where, if possible, you're able to interact across silos within the states to help people focused on risks to actually consider these kinds of risks that we're talking about today. So.
Okay, well, all right, one last question.
So from the state point of view, as far as design goes, a rainfall data table that would give you projections of rainfall data at the different service lives of the assets that we're building. So 50 years, 75 years, 100 years out. If we had a range of rainfall intensities that we could design for, then that's something that we could work with, and it takes all the politics out of it. It's based on historical records, latest genetic science, this is the estimate of the rainfall data. If an asset only needs to last 10 years, we probably don't care. But if a new bridge that needs to last 100 years, what's the queue that I need to be designing for? And it sounds like we're years or more away from a table, from a rainfall data table for various service lives developments. Because we can't go through a 10-step process for every different queue. And we're not going to do a climate study for every pole. It's just not.
Yeah, so this gives Stacey a chance to say something, because when we're talking about bridges, we're talking about regression equations and bigger things rather than just changes in precepts. So I'll let Stacey say a few things, and then I think we'll wrap it up after that.
I guess I'm wondering what you want me to say. More just about, do you mean the use of regression equations to estimate floods from precipitation?
I
or?
think there's still some way to go before,
Yes.
you're talking about
For sure.
projections in land use, wildfires, ground cover changes. You got to factor in the urbanization that's going to come anyways, all that stuff.
Right, so I think if that's what I'm commenting on, right, I think that those types of simple approaches are very attractive, I think, to be using, developing regression equations that you can then plug in a different precipitation number or a different build-out number. But I think that those simple approaches still need to be vetted pretty carefully, which is one of the hopes that we have as an outcome of the study, is really looking at the limitations of some of these very simple, attractive approaches to make sure that they have some level of robustness associated with them, and that the user can be confident that those relationships, say, between a precipitation event and a flood event hold. There is some literature now coming out, to say that a 100-year precipitation event does not equate to a 100-year flood. There's a lot of reasons why that's not the case. Antecedent conditions, someone brought out changes in seasonality. So if a lot of the rain is coming in the southeast in the fall, that's when flows tend to be their lowest. And so the ability to produce some large flood event does not necessarily equate to a large rain event. And so there is some thought that has to get put into how those things are actually related to one another when you look at these simple relationships. Having said that, I'm a firm believer in science. The most simplest method is the one I think that tends to be the most attractive, the one that's most useful to people on the ground. And so anything we can do to bolster the use, develop simple common sense approaches, as long as they're tested in a robust way, I think is something we should always be searching for as researchers, because that's, I think, one of the things USGS, I think I'm proud of, is that we develop solutions that fit that criteria. So, I don't know, hopefully.
I know it's not the answer you wanted, but
Sorry, I don't think that was at all the answer you wanted.
but that's, yeah. So everyone, thank you for attending, and I want to thank the panel and give them a big round.